fierce competition, I should say, among very amazing thesis research that is done here in MTL to make this very special presentation. So I'm very pleased today to bring you now Dr. Yuhao Zhang to give the doctoral dissertation seminar for the spring 2017. Since Yuhao was a sophomore at Peking University, he has been engaged in research in material science and electrical engineering. He joined MIT in 2011, and he did first his master's thesis with Professor Tomás Palacios, and more recently he has just completed his PhD thesis. And this is a tremendously important topic that Yuhao has been working on, which is how to make high-power transistors on gallium nitride that have a vertical structure. So as you know, there has been a lot of interest on gallium nitride, a truly revolutionary material now for several years, first in RF, more recently in power electronics, but all those devices are horizontal. And that is because the gallium nitride is built on silicon carbide or on silicon. It has many defects, so you cannot use the bottom portions of the gallium nitride. And yet, a vertical configuration is very beneficial from many points of view. It can be more compact, it can be cheaper, potentially can handle higher breakdown voltage. So Yuhao's thesis is about really coming up with concepts to turn the flow of electrons around and make it work in the vertical direction and take advantage that that geometry promises. And he has come with very interesting approaches to deal with the special issues that gallium nitride presents in the vertical direction. He has been tremendously productive in his research. He's published over 30 peer-review journal papers, has given many conference presentations, and has 6 patents issued or on file. It's really tremendous. In addition, he's also been exploring other interests, and he spent the summer, for example, at Mitsubishi Electric right next door here, which is something that I encourage all our students to do, to take 1 or 2 summers off and really explore other technical opportunities. So Yuhao, congratulations for this wonderful award, for being selected for this honor, and we're looking forward to your presentation.
Thanks very much for Professor Alamo's introduction, and it's a great honor for me to be here and to present my thesis work at this MTL Doctoral Dissertation Seminar. And hello everyone, my name is Yuhao, and I work with Professor Tomás Palacios, and my thesis work is mainly on the vertical gallium nitride power devices. So in my presentation today, I will first talk about the application and markets for the gallium nitride power devices. And then I will introduce 2 basic structures for the gallium nitride power devices, the lateral structure and the vertical structure. And then I will introduce some of my main works for the vertical gallium nitride power devices, including the electrothermal simulation, the demonstration of vertical gallium nitride devices on very low-cost silicon substrate, and the demonstration of the vertical gallium nitride advanced Schottky barrier diodes. And then I will discuss a little bit about the prospects and the future works in this area and conclude with the contributions and the summaries. So let's go to the first part. Okay, so this slide gives an overview of the applications of the next generation RF and the power devices. So there are a lot of very key and very important applications, including the 5G communications, the electrical vehicles, the energy efficient data centers, industrial electronics. And at the bottom, I show the applications of the power devices at different voltage levels. So we have the low voltage levels, typically below 200 volts, and the medium voltage levels and the high voltage levels. So we are very interested in the application at the medium voltage levels because there were 2 very promising markets here. The first one is electrical vehicles. So here I show the schematic of the main power architecture in these electrical vehicles to extract the energy from the battery into the motors and the generators. And the key component in this power architecture is a power transistor. To be more specific, we need a 600 volt to 1200 volt power transistor in this kind of the power architecture. And that will account for about 1/3 of total cost of vehicle power systems. And another very promising market is the data centers. So in the data centers, we need to step down the voltage from the electrical grids to the electrical loads. So typically, the voltage at the server host is 480 volts AC, and the voltage at the electrical loads are 1 volt DC. And in this power circuit, to step down the voltage, again, the power transistor is the key component. And it is also an important limiting factor for the power supply efficiency and power density in the system. And the total power consumption in the data centers all over the world is really huge. It has been estimated if we can just improve the efficiency of this power conversion by 1%, that can save about 10 nuclear power plants every year. And this is completely possible if we use next generation power devices. Okay, so the next question is why we think gallium nitride would be the best candidates for the next generation RF and power devices. There were two main reasons. The first reason, from a technical point of view, gallium nitride has superior material property than silicon. So for the application of the RF and the power devices, we mainly look at several key merits for the devices. We want the devices to operate at very high temperature. We want the device to switch at high frequencies. And we also want the device to have the high current and the high voltage, which allows for the high power. So let's see what silicon can give us today. So this green line shows the performance of the silicon. And the green line here is the gallium arsenide. So this is another 3-5 semiconductor that has been used in today's RF semiconductor devices. So it can give a little bit better merits compared to the silicon. And also, let's see what gallium nitride can give us. So basically, from here, we can say gallium nitride devices can give us a remarkable improvement in the operation temperature and operation power. And in addition, if we use the gallium nitride device and the circuit in a power module, then the switching frequency of this power circuit can be greatly enhanced. And this can also reduce the volume of other components in this module, such as the capacitors, inductors. So the total power density in this module can be greatly enhanced. So that's a technical point of view. And the second reason is from the business point of view. The gallium nitride has already achieved a huge success in the optoelectronics business. For example, the LEDs and laser diodes. So this would also make the market insertion of the gallium nitride power devices much more easier. Okay, and here I show the current market and market projection for the gallium nitride RF and the power devices. So basically, from here, we can see the gallium nitride discrete devices is already a $hundreds of million market right now. And here we show the market projection for the 200 volts and 600 volt gallium nitride power devices. Okay, so let's narrow down to the research of the gallium nitride power devices. And I would like to introduce two basic structures for the gallium nitride power devices. One is the lateral structure, the other is the vertical structure. So the representative device for the lateral structure is called the high electromobility transistor, the HEMT. And in the HEMT, we have the two-dimensional electron gas formed at the interface between the aluminum gallium nitride layer and the gallium nitride layer. And this two-dimensional electron gas can have very high mobility, and the device would have very low on resistance. And the main current path in this device is flowing in the lateral direction from the source to the drain. So this is called the lateral device. So this device also faces great challenges in the reliability and the difficulty to achieve the normally off operation. So on the other hand, we can also make the vertical devices. So the vertical structure has attracted more and more attention in recent years due to several advantages over the lateral device. So the first advantage is that the vertical device can achieve high current breakdown voltage without enlarging the chip size. So if we want to have a very high breakdown voltage in these lateral HEMTs, then we need to increase this gate to drain distance. So the device will be really large. However, in the vertical devices, if we want to have very high breakdown voltage, we just need to increase the drift region thickness, and the device itself can still be very small. And the second, typically the electrical field in the vertical structure is much more spreading and uniform compared to that in the lateral structure. So that allows for a better reliability of the vertical devices. And also the vertical devices would have the better thermal performance than lateral devices. Okay, So now I'm going to show you some of the recent progress of vertical gallium nitride power devices. So here at the bottom, this is the bar of the voltage class that demonstrated for the vertical devices. So in the last 3 to 5 years, there were 3 main categories of the vertical gallium nitride power devices that have been demonstrated. The first category is diodes. So there are 2 basic types of diodes. One is the PN diodes. The other is the Schottky barrier diodes. So the record breakdown voltage of the PN diodes is already close to the 5,000 volts. And we also have some advanced Schottky barrier diodes, which kind of combine the PN diodes and the Schottky barrier diodes in the same structure. So that's the first category. And all the diodes in the first category are demonstrated on the gallium nitride substrate. And this gallium nitride substrate are very expensive right now. So people are also looking for the low-cost solutions. So people are developing the low-cost vertical gallium nitride devices on silicon substrate. That's a second category. And for the third category, people also develop some vertical gallium nitride power transistors. So for the transistors, different groups are developing quite different device structures. So for example, the first transistor structure that's demonstrated is called a CAVIT. So this CAVIT, it is current aperture vertical electron transistor. So in this CAVIT, we still have the 2-dimensional electron gas generated at the interface between the aluminum gallium nitride and gallium nitride. And there is a vertical electric field to attract this two-dimensional electron gas to flow in the vertical direction through this current aperture. So this is the CAVIT. And this 2-dimensional electron gas in the CAVIT can generate it at the planar surface, as well as in the trench slopes. And if the 2-DAC is generated at the trench slopes, then basically it is called a trench CAVIT. And in this kind of a trench CAVIT, the very good thing is that we can modulate the threshold voltage of this device by changing the angle of these trench slopes. And the third device that has been demonstrated is the trench MOSFET. So in the trench MOSFET, the carrier channel is no longer the 2-dimensional electron gas, but just the MOS inversion layer. And this structure is very similar to the conventional silicon, the silicon carbide power devices. And at last, there is a very novel transistor. It's called the FIN MOSFET. So in the FIN MOSFET, the channel is this very, very narrow fins on top of a drift region. And these fins are typically like the 200 nanometers to 400 nanometers wide. So this is the FIN MOSFET. Okay, so in my own thesis work, I mainly focused these 2 parts, the advanced Schottky barrier diodes and the demonstration of the vertical gallium nitride diodes on silicon substrate. And I also helped Ming Sun, another student in our group, to demonstrate the FIN MOSFET. Okay, so next, let's look at the performance of the recent demonstrated vertical gallium nitride power devices. So typically for power devices, there are many working at 2 states. One is the off states, the other is the on states. So for the off states, typically the device has to sustain a very large reverse voltage, and we want the leakage current to be as small as possible. And at the on states, the device has to accommodate a very high current, and we want the on resistance to be as low as possible. And in a power circuit, typically the power devices will do switching between these 2 states. So that's why in the power devices, we mainly look at the 2 key parameters to evaluate the performance of power devices. One is the on resistance, and the other is the breakdown voltage. And we do this figure of merit for the performance evaluation. So in this figure, all these open symbols represent the conventional silicon and the silicon carbide power devices. And all this solid square symbol represent the lateral gallium nitride power devices. And all these blue ones represent the vertical gallium nitride devices. So if we look at the medium voltage applications, like from several hundred voltage to several thousand breakdown voltage, then basically we can see the vertical power devices has already achieved about 10 to 100 times lower on resistance, which is very good. But the price we pay for this improvement is the cost. So that currently, the vertical gallium nitride devices has a higher cost than the lateral devices and the silicon carbide power devices. So basically, the challenge for the vertical gallium nitride devices is how to achieve the high performance and low cost at the same time. So here I showed the schematic of the vertical gallium nitride power devices. So typically on the top, there will be a junction and a channel region. And in the middle, it should be the drift region. And at the bottom, it's a substrate. So there are several challenges for the carrier channel and the junction region. For the diodes, now we have the two basic structures, the PN diodes, which have very high breakdown voltage, but the turn-on voltage is also very high. And this very large turn-on voltage can induce a very large power loss during the switching. And we have another type of the diodes, is Schottky barrier diodes. The turn-on voltage is much lower, which is good, but the breakdown voltage is also much lower. So we need some novel structures trying to combine the benefits of these two basic diodes. And we also have the transistors. So for the transistor, it is still open question right now that which channel we're going to use for the transistors. The two-dimensional electron gas channel, the MOS channel, or the FIN channel, it is still open question. And also, there still lacks a very good edge termination technology for the vertical gallium nitride power devices. Next, if a vertical device is designed very well, then typically the drift region will determine the leakage at very high reverse bias and determine the breakdown voltage of these vertical power devices. So for the drift region, we need to understand the leakage current mechanisms and to understand what's the impact of dislocations and the impacts. And also for the substrate, it would be very interesting to know if it's possible to demonstrate the vertical gallium nitride on the low-cost silicon substrate. Okay, so now I'm going to introduce some of my main works to address these challenges. So the first work is electrothermal simulation. So 3 to 4 years ago, we developed some electrothermal simulation models for the gallium nitride power devices, both the vertical structure and the lateral structure. And we calibrated these electrothermal simulation models with experiments. And by utilizing these electrothermal simulation models, we basically can simulate the temperature distribution in the vertical power device and also in the lateral power device. And we can accurately find the location of the peak temperature in the vertical device and in the lateral device. And after this simulation, we would like to further compare the thermal performance of the lateral device and the vertical device. And to enable this comparison, we first need a figure of merit. We define the figure of merit P150 degrees C, which is the maximum power density a device can achieve without the peak temperature exceeding 150 degrees C. And then we designed the vertical device and the lateral device for different breakdown voltage levels and different scaling levels. And here we show the thermal performance comparison between the two devices. So the y-axis here is the outperformance of the vertical device than lateral device. And we plot this outperformance as a function of the design breakdown voltage and the scaling levels. So from here, we can see like the vertical devices can achieve a better thermal performance than lateral device. And this outperformance will be even more remarkable for the high voltage designs. And also in this electrothermal simulation, we assume the same thermal conductivity for the silicon and the gallium nitride, which means if we're able to demonstrate the vertical gallium nitride device on the silicon substrate instead of the gallium nitride substrate, we will still have this outperformance in the thermal. So the next step is to really demonstrate some vertical gallium nitride device. The main motivation to demonstrate the vertical gallium nitride device on silicon substrate is from the cost. So currently, almost all the vertical gallium nitride power devices has been demonstrated on the freestanding gallium nitride substrate. And this substrate is very expensive. So currently, the largest diameter for this wafer, gallium nitride substrate wafer, that can be purchased in the market is only 2 inch. And that will cost about $2,000 to $3,000 for per wafer. It's very expensive. So how to reduce the cost? One way is to demonstrate on the GaN silicon structure. So here it shows the wafer and the epi cost for different wafer structures. And here, this purple one is a GaN, and this yellow one is the GaN silicon. So basically, we can see if we're able to demonstrate the vertical device on the GaN silicon, we can have 100 times lower cost. However, It is not very easy to demonstrate the vertical gallium nitride device on silicon substrate. There are two main challenges. The first challenge is that typically the GaN on silicon structure would have much higher dislocation density, typically on the order of 10 to 9, which would be the 3 to 4 orders magnitude higher than the dislocation density in GaN. That's the first challenge. The second challenge is due to the lattice mismatch between the silicon and the gallium nitride, the total gallium nitride layers that can be grown on silicon substrate and transition layers are relatively thin. It's typically limited to 4 to 5 microns. And by overcoming these two challenges, we demonstrated the first GaN on silicon vertical diodes like 3 years ago. So this is the demonstrated vertical GaN on silicon vertical Schottky diodes. So we have a Schottky contact on the top, then we have a N- gallium nitride drift region, and then we have the N+ gallium nitride layer. This layer is called the current spreading layer or the current collecting layer. That will basically collect all the layer in the drift region to flow laterally to this cathode. And we have the cathode on the side forming an ohmic contact with this N+ gallium nitride layer. And then we have a semi-insulating gallium nitride layer is to prevent the vertical leakage. And then we have a transition layers in the silicon substrate. And similarly, we also demonstrated the PN diodes. The PN diodes has a very similar structure to the Schottky diodes, but the drift region will be the P-GaN layer and the N- GaN layer. So let's look at the performance of this first generation devices. The on resistance is 6 to 10, and although the drift region is not very thick, it's only 1.5 micron, but we can still get a breakdown voltage of 200 to 300 volts, which is really good. And also all these devices can operate at 150 degrees C without any degradation. So after the first demonstration, we have been working to optimize the device performance. First, we would like to reduce the leakage current. And in this structure, there were 4 possible leakage paths. The first one is go through this drift region, and then the N+ gallium nitride layer, and then to the cathode. The second one is a leakage path along this etching sidewall. Because this method structure is typically fabricated by using the very high energy dry etching, and this dry etching can induce a lot of damage and defects at the etching sidewall. So there might be a leakage path along this etching sidewall. So that's the second leakage path. The third one is go down to the substrate and transition layers and go back to the cathode. And the fourth one is go inside the passivation layer. And after some initial analysis, we identified this current path 1 and the current path 2 as the main leakage paths. So our target is to eliminate the current path 2 by having some new process. So the first process we developed is a nitrogen plasma treatment. So we found if we use a nitrogen plasma treatment right after the dry etching of this metal structure, then this nitrogen plasma treatment can heal the nitrogen vacancies, and this can lower the leakage current by about 1 order of magnitude. And the second process is the TMAH wet etching. So TMAH is a wet chemical which will etch almost all of the lattice planes of gallium nitride except for the C plane. So if we put this kind of a structure into the TMAH for some time, let's say for 1 hour, then the low quality side walls will be etched, but the total etching depth will not increase. And this method can give us another 1 order to 2 order magnitude lower leakage current. And the third process we use is the ion implantation. So we make some ion implantation rings at the edge of this ohmic contact and penetrate into the PN junction. And because this implanted region are quite insulated, so this can prevent the main current from flowing to the sidewall. And if we combine all these 3 different technologies, then we can lower leakage current by 2 to 3 orders magnitude. And we identify there is no leakage path along the etching sidewall. So after the leakage reduction, we also want to further increase the breakdown voltage. So in order to increase the breakdown voltage, we need to have thicker drift region. So we collaborated with Professor Armin Dadger's group in Germany, and they are able to increase this drift region from 1 micron to about 2.7 micron. And also we use some carbon to compensate the unintentional doping in this region. So here shows the profile of the acceptor or the donors in this GaN silicon wafer. If we don't have any carbon compensation, the donor concentration in this drift region is 3 times 10 to 16. And after the carbon compensation, it can be reduced to 1 times 10 to 16. Okay, so after the optimization of the reverse characteristics, we also want to optimize the forward characteristics. So we have done extensive TCAS simulation, and from the TCAS simulation, we found the sheet resistance of this N plus gallium nitride current spreading or current collecting layer is the key to reduce the total device on resistance. So here I show the simulated current density in 2 structures. In the structure on the left, it has a doping concentration of 10 to 18 in this N plus gallium nitride layer. And on the right, it's a doping concentration of 10 to 20 in this N plus gallium nitride layer. So as you can see here, the current is much more spreading in this structure, and the current density is also higher. That means the on resistance is lower. So we increase the doping levels from in our wafer in this layer from the 10 to 18 to 10 to 20. However, if we look at the structure here, even with the doping level as high as 10 to 20, the current distribution is still not completely uniform. This is limited by this quasi-vertical structure. So in this structure, we have the anode on the top and the cathode on the side. And this anode and the cathode are not completely overlapped in the vertical direction. And this lateral distance between these 2 electrodes will give rise to a non-uniform current distribution. So that means if we want to have the completely uniform current distribution, we need to demonstrate the fully vertical GaN silicon diodes. However, the direct fabrication of the GaN silicon diode is not very easy because these transition layers is very insulated and have a lot of the defects. So we demonstrate this fully vertical device by using a layer transfer technology. We first etched down to the silicon substrate in the original, like the GaN silicon wafer. And then we flip over the whole wafer and bond it to another silicon substrate. And we removed the silicon substrate and the transition layers in the original GaN silicon wafer. And we make another ohmic contact on the top. So from here, basically, we can see this top ohmic contact and the bottom ohmic contact are completely overlapped in the vertical direction. So this is a fully vertical device. So after all these optimizations, let's see what is the latest performance. So in the forward average characteristics, now the on resistance is about 0.8 to 1, compared to the 6 to 10 in our first generation device. This is almost 1 order of magnitude improvement. And also, if we look at the reverse characteristics, the breakdown voltage increased from 200 to 300 to over 500 in our latest result. And also, these devices can have the high performance, high temperature performance up to 300 degrees C. And if we look at the performance in this figure of merit, so this is our first demonstrations 3 years ago, and this is our latest results. So it's a already remarkable improvement from here to here. So our next step goal is to make our GaN silicon devices as closer as possible to the GaN devices. But we should also note here, like compared to the GaN devices, our GaN silicon vertical devices is 100 times lower cost. Okay, so after the performance optimization, if we go back to the leakage analysis, there is still a question left. So as I just mentioned, we have excluded the leakage path 3 and leakage path 4 in our initial analysis. And then we eliminated leakage path 2 by having some advanced process. So now the question is, what's the mechanism for the leakage path 1 going through this drift region? So for this bulk limited leakage conduction, we look at several possible leakage mechanisms. That includes the Poole-Frankel emission, which is thermionic field emission, and also some hopping conduction, which the carrier would do tunneling between the traps and dislocations in this drift region. and also some space charge limited conduction. And in this space charge limited conduction often happens in a structure with a lot of the traps. So the injected carriers will be captured by the traps and form some space charges, and the leakage current will be determined by these space charges. So as can be seen here, for these different leakage mechanisms, they have different relationship between the leakage current and the electric field. So we utilize these different relationships, and we also fabricated the gallium nitride vertical PN diodes on different substrates, the silicon substrate, the sapphire substrate, and on gallium nitride substrate. And then we also collaborated with Synopsys, the company, to build a lot of the simulation models. And after all this work, we're able to identify the leakage mechanism in the vertical gallium nitride PN diodes. So if we look at the leakage current density as a function of the reverse bias, typically at the low reverse bias, this leakage current might be limited by the electrode or the surface. And then the leakage current will mainly determined by this variable range hopping through dislocation, through the dislocations in the drift region. And if the structure has some defects, then at some point, there is a trap-assisted space charge limited current will turn on. And this trap-assisted space charge limit will determine the leakage path, leakage mechanism, and determine the breakdown the breakdown behavior. And if the device is really good, not much defects or dislocations, so it will be, this variable range hopping will continue until the onset of avalanche breakdown. So this is the leakage mechanism of the vertical gallium nitride power devices. And after we have all this, like the well-calibrated simulation models and experimental data, we're able to benchmark the vertical, the leakage, the design space of the leakage current in gallium silicon vertical devices with some other devices, like the gallium nitride lateral devices and the silicon carbide silicon devices. So here we plot the offstate leakage current as a function of the temperature, and here's the experimental data for all the other power devices. And this group of pink lines represent for the design space for the leakage current of the gallium silicon vertical devices. So basically from here, we can see the gallium silicon vertical device can have the comparable offstate leakage current, but with 2 times higher electric field. So that means if we want to have the same breakdown voltage, we can have much thinner drift region and much less material if we use the gallium silicon structure. Okay, so after the investigation of the drift region and the substrate, we continue to go up to look at the junction and the channel region. So as I just mentioned, there are 2 basic types of the gallium nitride vertical diodes. One is the PN diodes. The other is the short-gate barrier diodes. So for the PN diodes, the turn-on voltage is very large. It's higher than 3 volts. That is what we don't want. And the turn-on voltage in short-gate diodes is below 1 volt. It's very small. However, the breakdown voltage in this vertical device is much better. The vertical PN diodes are much higher than that in the vertical short-gate diodes. And this is mainly due to the different location of the peak electric field in these 2 diodes. So for the PN diodes, the peak electric field is located in the bulk gallium nitride at the PN junction. And in the short-gate diode, the peak electric field is located at the surface short-gate barrier. And if a peak electric field is located at the top surface, then it's very easy to be affected by the surface defects, surface dislocations, or the imperfect interface between the metal and the semiconductor. So that's why the short-gate diodes, the breakdown voltage is not as high as the PN diodes. So then it will be very interesting to think, is it possible to make some advanced short-gate barrier diodes which can still have very low turn-on voltage, but will move the peak electric field from the top into the bulk gallium nitride. And from this motivation, I designed a new device. It's called the vertical trench MNS barrier short-gate diodes, TMBS. So why it is called the trench MNS barrier short-gate diodes? Because we have a lot of the trenches at the top surface. And at the side walls and the bottoms of all these trenches, we have the dielectrics and the metals. So basically, we form a metal insulator and semiconductor MIS barrier at the sidewalls and the bottoms of each trench. And also we implanted some fill rings at the bottom of each trench. Okay, so now I'm going to show some simulation result to explain the concept design. Okay, so here it shows the simulated electric field distribution when in a device unit cell when the device is at a very high reverse bias, like 1,200 volts. So we have the two trench here, and we have the dielectric here, and this is the gallium nitride pillar, and this is the gallium nitride drift region. So if we look at the electric field along this car line here, then for the conventional Schottky barrier diodes, the peak electric field is at the top surface. And in this TMBS diodes, because we have this MIS barrier at the side walls, and this MIS barrier can have a strong depletion effect, so the peak electric field can move from the surface to into the bulk, and the electric field at the top surface will be greatly reduced. However, the price we pay for this movement of peak electric field is that we introduce two additional electric field crowdings at the trench corners. So how to solve this problem? We also implanted some fill rings into the trench bottom, and this can move the peak electric field from the trench bottom deeply into the bulk gallium nitride. So that's a concept for the design. Okay, so after some optimization, the fabrication of this device is not very difficult because we can use the same hard mask to do the trench etching and the argon implantation. And after the trench etching and the implantation, we remove all this hard mask, and we deposit the dielectrics everywhere, and then we open the window to make the top Schottky contact, and then we make the bottom ohmic contact. So the key process in this fabrication is the trench rounding and the shaping. Typically, after the dry etching of this trench, as you can see here, the surface and the surface of the side walls and the trench bottoms are really rough, and there are a lot of the defects there. So we developed a novel corner rounding process by utilizing the TMAH and the piranha clean. So after this novel corner rounding process, we have the very smooth surface inside this trench, and all these corners has been rounded. And we can further play with the dry etching conditions and combine these dry etching conditions with the corner rounding process. And then we can make a rounded trench with quite different shapes. We can make the rounded trench with a flat bottom. We can also make the rounded trench with a tapered bottom. And to decide which shape would be the best for the demonstration of the high voltage devices, we conducted some simulation. We simulated 3 trench shapes. The first one is the trench shape without any rounding. The second one is rounded flat bottom trench. And the third one is the rounded taper bottom trench. And from the simulation, we selected the second one as the shape to be used for the high voltage devices. Okay, so now let's look at the device performance. So we fabricated the Schottky barrier diodes, the trench MIS barrier Schottky diodes, and the trench barrier Schottky trench MIS barrier Schottky diodes with the fill rings. And if we look at the leakage current density for the 3 devices, then basically we can see the TMBS with fill rings can have a 4 orders magnitude lower leakage current and increase the breakdown voltage from 400 volts to 700 volts. So the reverse characteristics has been greatly improved. And if we look at the forward characteristics, all these devices would have a very good turn-on voltage below 1 volts. And the fill ring TMBS is a little bit slow in turning on. And this is because the impact of the implanted regions. But all the on resistance are quite decent value, 2 to 3 million centimeters square. Okay, so then we need to benchmark our performance with other vertical gallium nitride Schottky diodes. So for the vertical gallium nitride Schottky barrier diodes, people have found like this leakage current is very sensitive to the net donor concentration in the drift region. If this net donor concentration in the drift region is higher than 10 to 16, then the leakage current will shoot up very quickly. And unfortunately, the wafer for our devices has relatively high donor concentration. It's a 2 times 10 to 16. But by having all these TMBS and field ring structures, we're able to lower the leakage current by several orders of magnitude and make this leakage current comparable to the devices with a 10 to 15 level donor concentration. And also, if we look at the figure of merit of the unresistance breakdown voltage here, and we demonstrate the second best performance, and also we demonstrate the first vertical gallium nitride Schottky rectifier that can be operated at very high temperature, above 250 degrees C. Okay, so the device we just demonstrated is a 2-terminal device. So they have the trench has an MIS barrier, and if we add another electrode, but still use this trench structure, still use this MIS barrier, then basically we can demonstrate a new transistor called the FIN MOSFET. So for the FIN MOSFET, we have the source on the top, we have the gate and the gate electrics here, and the drain at the bottom. And for the FIN MOSFET, we further shrink this width of this gallium nitride pillar down to the 200 nanometer to 400 nanometer. So due to the strong depletion effect of this MIS barrier, then basically this device can achieve the normally off operation without the need of the P-type gallium nitride. So that's a FIN MOSFET. Okay, so now I'm going to discuss a little bit about the prospects and the future works of the vertical gallium nitride devices. So I think the target for the vertical gallium nitride power device is to enable the commercialization for 1200 or beyond applications. And in order to achieve this target, we still need much effort. For the carrier channel and the junction region, we need to further push the limit of this advanced Schottky barrier diodes. And for the transistor, we need to make a very wise selection of the channel, the 2-deck channel, the MOS channel, the FIN channel. And also, we need to develop a very good edge termination technology for the vertical gallium nitride power device. And for the drift region, for the material scientist, it's very important to lower the net donor concentration in the gallium nitride drift region down to the 10 to 14 to 10 to the 10 to 15 level. This is the key to demonstrate the several thousand volts applications. And also, it's possible to demonstrate some novel structure for this drift region, such as superjunction. And for the substrate, there are 2 main next steps. The first one is that we need to further lower the cost of the gallium nitride substrate. Is it possible to make it larger and cheaper? And also, we need to further push the limit of the GaN silicon vertical devices. And next, I will just go over very quickly about one very important future work. It's a demonstration of the gallium nitride power PN junction, pattern PN junctions. So what is the lateral pattern PN junctions? It's shown here. So basically, we want a lot of the PN junctions buried into the gallium nitride layer. And this PN junction has to be formed in the lateral direction. And why is this pattern PN junction very important? Because this is the most key component for the successful silicon and the silicon carbide power devices. So for example, if we have this pattern PN junctions, then we can make very good edge termination, and we can make another very good advanced Schottky barrier diode called the junction barrier Schottky diodes. This is a very successful silicon carbide power device. And also, with this pattern PN junctions, we can make the super junction device, which is one of the most successful silicon power devices. However, the demonstration of the pattern PN junctions is not very easy. It's very important, but very challenging. And in the last year, we have been, from the last year, we have also done some preliminary work to fabricate the gallium nitride pattern PN junctions. And here, I would like to show some preliminary results. So basically, we try to use 2 methods to make these pattern PN junctions. The first one is that we implant a lot of the P-type ions into the N-GaN region. Another method is we first grow a PN structure, and then we implant the N-type regions into this P layer. And then we make the junction barrier Schottky diodes. And as you can see at the forward characteristics, the turn-on voltage is really good. It's below 1 volt. it's a 0.7 volts, so it's still a Schottky. And for the reverse characteristics, it can have a higher breakdown voltage and lower leakage compared to the Schottky barrier diodes. But all these are very, very preliminary, very early stage experimental result, and we are currently still working in this very important issue. Okay, so I'm now going to conclude with the contributions and summaries. So the first part of my thesis work, I demonstrated the GaN silicon vertical devices, and demonstrated it is promising for the 600 volts level low cost, high current, high temperature power applications. And also, in the second part, I demonstrated some advanced vertical gallium nitride Schottky diodes, which has the Schottky-like forward characteristics and the PN-like reverse characteristics. And I also unveiled the original design space of leakage current in vertical gallium nitride device on different substrates. And besides all my work on the vertical gallium nitride devices, I also have done some other works, including some simulation work on the diamond gallium nitride integration, and then some new method to fabricate normally off gallium nitride HAMs, and also some electrothermal simulation. And here is the main conference presentation I have made during the last several years, and also the several patents I have filed with my research advisor at MIT, Thomas Palacios, and my research advisor during my intern. And at very last, I would like to acknowledge a lot of people. First, I would like to thank Professor Thomas Palacios. He's my research advisor, and it's very fortunate for me to work with him in the last 6 years, and I really learned a lot from him. And I also would like to thank Professor Alamo and Professor Perut and Professor Antoniadis in my thesis committee and RQE committee. And then I would like to especially thank my close collaborators in the group. It's Ming Sun and Daniel at MIT, and the Zihong in the SMART program in Singapore. And then I would like to thank all my collaborators outside MIT, including the Professor Nicola Gangrang's group at EPFL, Professor Armin Dedeker's group at Germany, and Dr. Teo, he's also here today, at the Mitsubishi Electrical Research Lab in the US, and Hyun Yong from Synopsys, Xiang from IQE, and Chris from Applied Materials, Marco from Naval Research Labs, and Professor T.P. Ma's group at Yale, and the company Increase from China. And then I would like to thank all the staffs at MTL. They helped me really a lot for the fabrication, and I think none of my work can be done without their helps. And very last, I would like to thank all Palacios group members, my friends at MIT, my parents, and my girlfriend for all their support in the last 6 years. Thank you very much.
All right, we'll take some questions now.
You have a big family. Anyway, a question on your thermal simulation. First question is, in your thermal simulation, is it a 2D or 3D simulation? Right? That's number one. Number two, how do you experimentally verify the hotspot, the location of the hotspot?
Okay. So first, let's see. So for the first question, this electrothermal simulation is the 2D. It's 3 to 4 years ago. But I think in the future, we need to have the 3D, especially for the multi-finger devices. It's very important. And the second one is, at that time, we calibrate with the experimental result, mainly by the calibration with the IV curves, by considering all the thermal effects. And also, we build a thermal reflectance system in our lab to try to accurately see the temperature and measure the temperature distribution in the real devices. And we're still improving like this experimental setup. And I think in the future we need to also calibrate the simulated peak temperature with the experimentally measured temperature. Yeah.
I want to ask you about this, if I understood correctly, nitrogen plasma treatment.
Yeah.
To improve the cycles of your trenches or your fins. Did you characterize in what way it changed the surface? What was the problem that you had, and how that nitrogen plasma treatment improved things?
Okay. So we think the improvement mainly comes from the heating of the nitrogen vacancies, because we actually utilize two. One is the nitrogen, the other is the hydrogen. So it has been reported like the hydrogen will create a lot of the nitrogen vacancies for the plasma treatment, and the nitrogen will heal these nitrogen vacancies. So from here, basically, we can see this is without any plasma treatment. And if we have the hydrogen, then we have several orders magnitude larger leakage current. And if we have the nitrogen plasma treatment, then basically we have the lower leakage current. But I think more detailed material characterization in the microscopic scale would also be very helpful for the next steps.
What was the temperature of this?
This is just a room temperature. Yeah.
And what tool?
Like plasma quest, like that. Yeah.
Thanks. More questions?
Excellent work. In real application, the power management will be limited. So between a vertical device and a lateral device, what do you think is which one is easier to do the thermal management?
Okay. So I think basically, undoubtedly, the vertical device would be better for the thermal. And fundamental kind of a intuition is that for the lateral device, basically the current flows in a lateral direction. So the heat generation is generated in the lateral direction, but the heat dissipation is in the vertical direction, because most of the heat actually dissipated through this way. So it's not in the same the direction, and also the heat generation area is very crowded near the surface. But for the vertical devices, the direction for the heat generation and the heat dissipation are actually consistent. So that's why it's a more suitable for the heat generation. And also for the package, most of the package, basically we extract the heat from the bottom. So that means it will be much easier to extract the heat from the vertical device compared to the lateral device. Yeah, sure.
Is there a fundamental reason that heat cannot be extracted from the top?
I think people are also trying to develop some method to extract the heat from the top by using some new package schemes. But I think the main challenge here is that typically, especially for the lateral device, I think for the vertical device it is totally possible. But for the lateral device, because this two-deck channel is very close to the surface, so even if we have a lot of the passivation layers, but if we have something which changes the stress of this two-deck region, then the performance of the device will be significantly different. So I think that's the main obstacle in extracting the heat from the top for the lateral devices. But for the vertical devices, I think it will be much easier to do this.
Sorry, Doctor.
Yeah, sure.
The distribution of your heat here, did you use any heat sink by any chance in this case?
Oh, yeah.
Did you, in your simulation, assume any heat sink?
Yeah. So for the simulation, we basically assume there is a heat sink at the bottom, only at the bottom.
So that may be the contribution to why the heat is moving down.
Because that corresponds to the real applications. Yeah.
So if we flip, right, using flipping,
yeah.
If the heat sink on the top as opposed to the bottom, I guess the distribution of heat will be different.
Yeah. I think it will be a very interesting thing to look at. And for the other thing is that even if so in the real applications, actually people are kind of will thin down this substrate to make the heat extraction closer to the channel region. So typically, I think for the GaN silicon in the lateral device, they will thin down the silicon substrate to tens of microns. Yeah.
Any more questions? All right, if not, thanks again.
Yeah, thank you.
We can now officially give you
the
award. So congratulations, don't
Yeah.
put on your foot.
Thank you.
I want
Yeah.
to fix also the comment section.
Thank you.
Thank you.
Thank you very much.